Hello, so just a quick introduction to our lab report. What happened in this lab was we basically analyzed, real-time modeling of an object's motion, um, and we used ultrasonic sensing technology to do so. So what this sensor basically measured the time it took for the object, for the sound to travel to the object, which is in this case was us as students, and back to the sensor to determine its overall distance. This is really a good device, to determine an object's distance, as I've said, and overall to interpret position versus time graphs.
So, what does the recent literature tells us? In my findings, by Wu Tong Wei, um, this literature review stated that the application of these sensors can really be explored within two sectors, automotive and agricultural. Um, some examples are parking assistance, surveillance of crops, irrigation management. And, these sensors have really increased growth and innovation within these sectors. However, we must, weigh the pros and cons of it, meaning that it is more cost effective, but it is and it is reliable for short range. However, a downside of this is long range is limited, and, cases of bad weather can decrease accuracy. So, as we saw in the literature, these sensors are you know, they could be obviously applied in real life, as we said for, automotive systems. You know, they can help in detecting blind spots when parking, for example, and agricultural applications, such as crop growth. As I've mentioned, making sure adequate, amounts of fertilizer is being applied to overall reduce pollution or any waste or wasting any of the product. So really, this is an innovative tool, and I also wanted to note that this can also be a tool within the medical field. You can, healthcare providers may use this as a diagnostic tool, in diagnostic imaging, such as, detections of maybe diseases, tumors, or just, overall movement of internal organs during surgery. It's really an innovative way to problem solve.
So I will be presenting the materials section. Um, this is are all the materials that we use to carry out this experiment. It required the use of Pascal, otherwise known as Capstone, and this is an application in computer software. It was used to document and create the position versus time graphs that will be displayed later on in this video. A motion sensor, Passport, and it was used as a tool to sense human motion and convert it into data. A laptop for observations and data, and we used what we would call like an object, which is using ourselves to display how an object would the slope that it would have in a position.
During this procedure, the way we started out is first we turned on the passport sensor and then the capstone application on the computer. Once we were logged in and familiarized ourselves, we opened it to the graph so that way it was already up in front of us. So once we started the experiment, it would record properly. Then we picked the proper device in order to get the experiment properly recording. At first, we tried our cell phones and then a notebook. And then from there, we just moved on to using ourselves. After clicking onto the application, we face the sensor in the correct direction and calibrated it, which is very important to do so between every trial to keep the recordings as accurate as possible. So once we did one recording, we would examine it, and before we moved on, of course, took a picture of the graph, and then again erased the recording, recalibrated the machine, and then started again from zero, depending on which graph it was. If we had to be farther away or closer, depended on the graph. Once the sensor and the application was ready, we began the trials with attempting to replicate the first graph. The first graph was following, going away from it, the sensor, then staying in place, stopping so it would go flatline. From there, it was going towards the machine at a fast pace, so that way it would rapidly decline. And then from there, we ended the recording, so that way it would end off on that one particular point that we wanted. During the recording of the first graph is when we ran into some issues with the sensor that we originally had. We did complete our first graph on that sensor, but afterwards we did move to another sensor. That second sensor is where we did graph 2, 3, both of graph 4 and graph 5. After that, we just continued using our bodies to create the recordings of the graph. The recording of the rest of the labs was made the same way, following the graph for step one, whether it was starting out farther away or closer, and then following the rubric of moving closer to the sensor to make it go down, or moving farther away from the sensor to increase the slope. And that's how we created the graphs. In the next slide, we show a video of how we made how our movements were done to create the graph. Data and data analysis. This is our graph 1. The key is 1, going away at a slow pace. 2 is a steady and stopped. 3 is going towards at a fast pace. And then 4 is the end of motion. So for graph 1, it follows 1, we're going away at a slow pace. 2, we're stopping. 1, again, we continue moving away at a slow pace. 2, we stopped. 3, we quickly went towards the sensor. And then 4, we stopped again in front of the sensor and ended the graph there. That's how we created the steeper slope going down for this graph. For graph number 2, our key is 1, steady, stopped. 2 is moving towards the sensor, and 3 is moving quickly away from the sensor. So for graph number 1, we start out with 1, steady, stopped in front of the machine, the sensor. 2, we're going towards it, causing the decline. 1, we stop, again, causing the flat. 2, we move towards it, causing the decline. 3, we quickly move away from the sensor. And then 1 again, we stop, causing the flat. For graph number 3, we started at a farther distance, but the key is 1 is steady and stopped. 2 is moving towards the sensor, and then 3 is moving quickly towards the sensor. So for graph number 3, we started 1 from far away, and it was 1 steady stopped, then 2 moving towards the sensor, causing the gradual decline. 1, we stopped again, causing the flat. And then 3, we quickly moved towards the sensor, causing a steeper incline. And then 1 again, we stopped, and it caused the last flat for the sensor. And that's how we created graph 3. So we were just moving towards continuously, and overall our graph was just decreasing as we got closer to the sensor. Graph number 4, data and data analysis. Our key is 1, moving away from the sensor, and then 2, moving towards the sensor. Both of those are quickly to cause the up and down motion. So number 4 reads 1, moving away from the sensor, causing the uphill. 2, moving away from the sensor, causing the downhill. Again, 1, moving away from the sensor, causing the uphill. And then 2, again, moving away from the sensor, causing the last downhill. This is graph number 4. This is also the one that is shown in the video prior to this slide. Graph number 4, this one, we didn't have any errors with like how the. For graph number 5, our key is 1, steady stopped. 2, moving away from the sensor. 3, moving towards the sensor quickly. So for graph number 5, we started steady and stopped in front of the sensor. We did 2 moving towards the sensor, then 3 moving away from the sensor, then 2 again moving towards the sensor, then 1 where we stopped moving to cause the flat, and then 2 where we're moving again away from the sensor, causing the uphill, the last uphill, and then 3 is moving away from the sensor, and that's how we ended graph 5 with a sharp decline as we're moving away from the sensor. Moving towards the sensor.
So, to conclude, in this lab, we learned the correlation of movement when creating position versus time graphs. We did it hands-on through creating graphs based on our own movement. Making the position versus time graphs helped us understand how an object's position changes over time and how that change can be represented through lines in a graph. The equipment we used was a passport motion sensor, and our initial sensor wasn't picking up, or if it did, it wasn't accurately representing the movement we did or the objects we tried to use. To address this, we recalibrated and we moved the sensor along the beam to lessen the amount of spikes we had, which was quite a bit. We also attempted each graph multiple times, and we ended up switching over to a better sensor in the end, which better accurately described our movement. And lastly, our values weren't exactly matching the graphs we were supposed to recreate, but overall it had the same changes of direction and speed.